I'm going to take you through a little bit of background on Aerospike and Docker. Then we'll show you a demo of how you can take a simple container application from development all through to production. And as you're going through those steps, adding in the additional requirements that you always have as you add in HAProxys, load balancers, and other production requirements, and how you can supplement your Docker configuration as you go along. So let's make a quick start. So for those of you who are not familiar with Aerospike, really the bottom line is we provide a key value database that typically gives our customers 10x improved performance over their existing database solutions. And that could be another NoSQL solution, or it could be another traditional relational database with a cache. So that's a great claim. How do we do that? We fundamentally build architecture top of this diagram, which is doing processing. It could be front-end applications for your users. It could be doing real-time decision making. What you'd increasingly have to do is, in front of your operational database, put layers of caching as a caching tier or thread caches in your application code in order to ensure that you have immediacy of data to its use. And what you're really trying to do is build engaging and rich applications with data with lower latency in order to create those compelling applications. You may be supplementing your operational data store with either machine learning or analytics you've done in your analytic layer, but at the same time, it's getting increasingly more difficult to build these type of applications as the needs for your data go up and the latency requirements go down.
Muted.
As you can see in the diagram, where you have your operating file system cache, your page cache, your block interface, you have many layers that you have to go to before you can actually get to the disk or the SSD. In Aerospike, what we have done is we built our own proprietary log structured file system, and what that means is that we can directly address the block device. It means that we take out those layers of inefficiency in the stack, and what it allows us to do is to dramatically parallelize the reads and the writes to that infrastructure. And this is some of the proprietary technology that gives us this order of magnitude improvement in performance. So let's have a quick talk about use cases where Aerospike gets used. One of our sort of traditional segments of use cases is around ad tech. These are the companies that are either placing adverts onto your web browser or into Facebook, or these are the organizations that are bidding for the right to go place those adverts. Now, from a very early start in 2010 and 2011, what these organizations have found is that they need to process larger and larger data sets in order to provide the right placement of the right advert to the right user. This means that they have very low latency requirements. They typically need to place an ad after a bid in 75 milliseconds, and they're tracking literally billions of cookies on hundreds of millions of users. You know, their job is to try and understand the household, the consumers within that household, and the devices you use within that household, so that they're placing the right advert to you. As you can see on the right-hand side, there is a large number of advertisers, publishers, exchanges that all use Aerospike as their core database platform. These guys not only need low latency, they also need extraordinarily high availability. If Aerospike is not up, then they are unable to actually make money. And so these are mission critical use cases where Aerospike is used. Another great example of a use case for Aerospike is in fraud prevention. So you can imagine you're swiping a credit card at a kiosk or an airport terminal to buy a coffee, and it's really nice if that credit authorization goes through. There's nothing worse than standing there and getting a denied. Now, typically when you start traveling, all of a sudden you've swiped your credit card in San Francisco and now you swipe it in London 12 hours later when you've arrived, and this causes traditional systems a problem because you need to really access a larger set of information to understand that this really is the same person, this is their 5th trip to Europe this year, and by the way, they've already actually paid for this trip with the same credit card. And so you need to correlate larger sets of information. And this is a use case from one of our customers who takes what they learn from their analytics, from their Hadoop infrastructure and their machine learning. They feed that back into Aerospike, and they blend that with the transactional data that's coming in so they can make better real-time decisions. So that's a couple of use cases. Let's quickly move on to containers. So containers logically seem like they're a new thing. They've been around for some time, and the underlying technology has been around for some time too. If you look at the kind of core mission that Docker and the rest of the container industry is trying to achieve is they're really trying to reduce the complexity of going from build, ship to run. One aspect of containerization is that it encapsulates all of the dependencies that you need in order to execute this piece of application. So you know which operating system and which version of Python and which other packages have to be installed. And this means that you've got a very simple way from running on your development machine through to the test machines into production using the same set of dependencies and the same OS release. You're not spending time trying to debug production, trying to understand if all the dependencies are the containerization is that it gives a simple way to manage your workloads at runtime. Traditionally, perhaps you either ran this on bare metal, in which case you ran each one of these workloads physical machine. Well, that obviously led to inefficiency, so virtualization became a way to consolidate all of those workloads onto a fewer set of machines. Unfortunately, virtualization is a very heavyweight solution to essentially what is a problem about ensuring isolation of processes. And so containerization is a solution to that. There is an open container initiative. As you can see, lots of people have signed up from that, from the likes of Docker and CoreOS to the likes of VMware, Red Hat, and so on and so forth. So there's a lot of industry backing in order to make not only containers intuitive to use, but you can actually gain portability and interoperability up and down the stack with them. So that's a little kind of primer on containers. So let's combine Aerospike and containers. What does that really mean? Well, we think Aerospike is a really interesting database solution, especially when you combine it with containers. So as people march towards, service and microservice architectures, you're trying to combine the processing, the data storage, and the messaging that you need to deliver the service in a set of discrete containers. Aerospike has some tremendous advantages because with its shared nothing architecture, it means that every node or every container is equal in an Aerospike cluster. There aren't special nodes that have special monitoring powers or configuration powers. All those nodes are equal. Inbuilt into Aerospike, we've got the ability that when a new node is added into a cluster to automatically rebalance the data within that cluster. So there's no administration steps you have to do once that node enters the cluster. From an application point of view, again, we've simplified the task. Our clients, which support all the popular languages, Python, Ruby, C, C#, and so on and so forth, they all have the ability to automatically detect the cluster or the topology of the Aerospike cluster. And what this means is, as that cluster changes over time, the Aerospike clients automatically detect those changes without you needing to write any specific code in your application. And again, this greatly simplifies the kind of flexibility that containers provide without needing to add additional complexity into your application tier. So that's why we think they're a great match. We also think they enable you to scale up. It's easy to now move your containers onto larger hardware configurations or to scale out so that you can add more nodes into this cluster. As we said earlier, it eliminates some of the manual reconfiguration and manual sharding that you may have to do on your existing database solution. And what this really allows you to do is exploit not only the bare metal you may have in your infrastructure, you can also run this on public clouds with little or no change. So that's the kind of, the backdrop. What do we want to spend our time today is really kind of walking through a demo. You're going to witness me mistyping many, many commands, and I'll do my best to eliminate as many of those typing mistakes as I can, but this is a real demo. Hopefully everything will work through, but with a real demo, there's always the possibility that things are going to fail, and so bear with me if we do hit any hiccups. What we're going to try to do is we're going to start off with a very simple application which we're going to run in our development environment, and then we want to take this application through a deployment scenario where we're going to scale our web services and scale the Aerospike cluster. And what we can see is we can inject behavior all through those steps that allow our DevOps team or our operations teams to ensure that as we go from development to production, we can adhere to all of those standards of those different. So let's start off with something simple. We're going to create a very simple Python Flask App, and it's going to use Aerospike as its database. What we want to end up with is an application that scales out. What we're going to do is we're going to put HAProxy in front of the application servers. So that means that we can scale out the application servers on demand. And then what we want to do is scale out the Aerospike cluster underneath as well. So that's the kind of where we're going to start. This is where we're going to end. So let's do the first part. Let's go and build an application. So let me take you over to my editor. See, we have a very simple Python application. So this is just you. We connect to our Aerospike database. Each that is going to be served, we make sure we're connected to the database, and then we're going to insert a few records, and we do that with our put method. And so we're going to record each time we enter this page, and then we're going to increment 2 counters, and then we're going to retrieve a record, which is the summary. So each time we enter this page, it's going to do 1 insert, 2 updates, and 1 query. So let's get the application up and running. And I'm using Docker Compose, and Docker Compose I've used to encapsulate our web application and our Aerospike server. So as you can see, that's up and running. So let's go and have a look at our most awesome application. So if I do a page refresh, as you can see, we've just created the world's most awesome page counter. So each time I refresh this page, we can see the counter going up. So how did we orchestrate those services? Let's go and first look at my Docker file. So if you've not seen a Docker file before, what we're trying to do here is describe all the things that we need for our application code to work. So the first line is saying that we need to use Python, and we're going to use a concrete version of 2.7. I'm now going to add the source code from the .py file and a set of patterns I'm dependent on, that's libssl and Python dev. And then I'm then going to run pip install to ensure that all of my Python dependencies are installed. I'm going to expose port 5000. I'm going to run the Python command. So that's kind of encapsulating everything I need to run my application. I'm then going to put this all into a Docker Compose file. So here's our Docker Compose file. What we can see is we've got two services defined. We've got Web and we've got Aerospike. And inside our web service, we're going to provide the command on how to build this. We're going to also describe which ports we want to open and where they're mapped. We're going to describe a link to Aerospike, and what this will do, link those two containers so that they can communicate over the network. And we're going to set a couple of environment variables. On the Aerospike service, what we're going to do is first indicate that we want to use the Aerospike server from the Aerospike GitHub, and so this is the official image that Aerospike provides for the server. And what we're doing is also we're specifying the latest version. We're not going to narrow it down to anything specific. I'm a developer, of course. I want the newest and the most awesomest version there is. So that's what I'm going to use. And so that's kind of how we have composed this service. And so that's really great. And so we now have our working application, which we've built, we've demoed. And I've just spoken to my dev manager, and he thinks we should ship it. And I think that's the most awesome news as an engineer I've heard this week. But now I've come and talked to my ops team, and my ops team, they think this is pretty awesome as well. But they've got a couple of additional things they want to ensure. They believe just having one application server may not be enough for us to deal with their anticipated workload. So what they'd like to do is run the application server behind HAProxy. And so this is just a simple load balancer that allows the ops team to add in more application servers as the demand goes up. And obviously they can then go and add as many as they need. Now, we also want to do potentially the same for the Aerospike server. At some point we may run out of the number of queries or writes per second that a single server can provide. And like many NoSQL solutions, Aerospike is designed to scale out across horizontally. So let's talk a little about networking. Clearly for a production deployment, you're going to run these containers on more than one physical server. So what I've described here is essentially 4 servers, Swarm 0 through Swarm 3. Now, inside each one of those servers, we're going to have a number of containers running. But those containers are going to need to communicate with each other. And so we have 2 networks defined. At the top, we have our bridge network, and that's the network that is going to be exposed to the outside. So we can take incoming web requests, HTTP requests. Our second network at the bottom, the prod network, this is the internal network that the Aerospike nodes communicate across, but it's also the nodes that our web containers will go and query and insert and update data to. That we're aiming for. So let's actually go and do that. Let's go back to our terminal. We don't need our development one anymore, so let me just shut that down. So let me first a new orchestration. And so what we'll see here is we're going to have 4 services. We've got HAProxy, our web service. We've got Aerospike and a new discovery service. And just to show you that these all look the same, Let's go onto our new page, and this is our browser pointing at production server. And as you can see, the functional behavior is from dev in production. A little graphic, and this is a little app that was created to show the current topology of stuff. Swarm 0 and Swarm 1, and you can see our database, and you can see our application. As our next step, what we now need to do is we now need to ensure that it matches the topology we've just described. So let me just attach to the prod network our first container, which is HAProxy. HAProxy1. And there you go. This is just to prove this is a live demo, and I mistyped commands. Okay, so we've now connected Let's attach our discovery node to this same prod network. So let's do the first fun thing. Let's now scale the web service. So let's go and add 5 new application servers. We want to ensure that we're meeting the needs of that incoming traffic. So as you can see, those 5 are starting. And if you go back to our visualization, you can see those new application servers starting. And our application carries on working as we have scaled each one application behind the HAProxy. Database. And then what we can do is we can query the database. So let's just log on to the network prod. We are going to run Aerospike, and we're going to run the tools image. We're going to run a utility called AQL, which is just a command line utility that allows us to inspect the contents of the database. And then we are going to connect to prod Aerospike 1. Now this is kind of really interesting because, oh, and I've mistyped. This is really interesting because one of the things that multi-host networking gives you in Docker, all of these container names are now host names. So we can show in a second these container names, but I can actually the concrete orchestration. I can use those same names. So if I just query the database, we can see here are all of our hits on that web page, so it looks pretty good. And I can also pull from our summary table, and as you can see here, we're collecting the IP addresses of each one of those web servers and the total number of hits. See each hit after we scaled out. So that's pretty interesting. As I said earlier, if I do a whoops, we can actually see all of those containers running, and the screen is slightly behind. There you go. And then you can actually see on the right-hand side the name of these containers, prod Aerospike 1, and that's the concrete host name. So we've done the first part of the exercise, which is we've scaled the web tier and scale the Aerospike cluster. Let's just assume we're now running out of the ability to read and write data. We need to now scale horizontally. So let's let's demo that piece. Now, if I go back a slide, the key thing here we want to do is we want the ease of operation as new Aerospike containers start up. We want to ensure that they are included into the Aerospike cluster, and the cluster knows that those new nodes are present. So let's start that up. So let's now scale Aerospike, and let's add a second node in. Okay, that's all started. Now, if we look back on our topology, we can actually now see that there are two database containers up and running. So that's good. And if we carry on refreshing our web page, we can see that our web application is still running as expected. So just to confirm that that topology has taken effect, we can now run another Aerospike utility, ASADM. So Aerospike tools, ASADM, and we're going to execute the info command, and we're going to give it the same host name as before. Okay. We'll give that a second to run, and I have mistyped. Oh, there you go. It helps if I specify the name of the image correctly. So what the ASADM command doing is when we ask it to get us the info message, what it will do is it will go out and discover what the topology of the Aerospike cluster is, and will report on each one of those nodes. And sometimes that can take, a few seconds to run. So whilst that's doing that, let's have a look at the code behind this. Oh, there you go. It returned before I could go. So you can see we've got our multiple Aerospike nodes here. You can see the IDs, the IP addresses, the uptime, and so on and so forth. So you can see that this cluster has automatically been expanded. So let's have a look to see how we did all of that. So let's take a step back, and going back to our compose file for production, we've got our 4 services defined for HAProxy, for web, our discovery service, and for Aerospike. So we're using the ability in Docker Compose to extend services. So HAProxy simply extends from haproxy.yaml, a particular service, and we'll dive into that in a second. Given that this is our production system, our ops team wanted to ensure that proxy runs inside that swarm cluster. So what I can add is a constraint or an affinity rule for that particular service that says a node called swarm 0. So what we're now doing is we're pinning particular containers to particular parts of that topology. Here we have our web container, and we can see it's going to use this application image that we've pushed. Again, it extends from HAProxy, and it's going to define the node that we want to talk to in terms of for our clustering. We've also said that by default, this container is going to sit on our prod network. Finally, or almost finally, but last, we have our discovery service. This extends our cluster YAML file, and we'll talk about that in a second. It defines some environment variables, again defining an affinity rule. And finally, at the end, we have our Aerospike service. And this is going to pin our usage of Aerospike to a specific version. So typically when you're in production, you just don't want to pull the latest version of a piece of software. You may want to pull a very specific version so that as you start new containers, you're not using mixed versions of Aerospike, you're using a concrete version across the whole farm. And we're going to add an additional affinity rule, which says that, as you can see here, we define a label, and the label is com.aerospike.cluster. It could be anything, and we define this particular value of awesome counter because our application is the awesome counter. Our affinity rule simply says that when the placement of this container inside the Docker swarm, there can't be another Aerospike container running. So what this guarantees is that for any given Docker host, there is only one and only one Aerospike container running. And so this means that if you lose the whole Docker host, you'll have the least amount of outage because you're only running one Docker process per host. Of course, you can supplement whatever rules make sense in your infrastructure. So let's have a look at those files that we extended from. Again, this is a great way to encapsulate a sort of core needs, and then as you go through the various stages, extend or supplement. So in our HAProxy, we are using an image called Interlock. And Interlock was created by Evan Hazlitt. He's over at Docker. And Interlock is a really great and interesting technology. Essentially what Interlock does is it listens on the Docker network bus or event bus for events like a container starting or a container stopping. And he's built a framework where you can build plugins. And my colleague Richard, say hello, Richard.
Hi, everyone.
Richard built our Aerospike plugin. And so essentially what this does is it looks for a container starting that are running Aerospike, and then it'll automatically add those containers into the cluster. So we use Interlock both for our HAProxy, because there's a plugin for HAProxy, and we build a plugin for Aerospike, so that we can manage flexibly those two pieces of infrastructure we want to scale out. If we look at our base cluster, again, you can see our discovery service is running Interlock, and it's running Interlock to see these events to automatically configure the Aerospike cluster. And then you can see our Aerospike service at the end. And so the combination of using Interlock and using the containers to encapsulate the load we want to execute, we've got a very simple and easy way for you to scale up and to scale down or scale out your cluster. So let's quickly jump back to the slide. So we've managed to scale our web tier and our Aerospike cluster. The great thing there is that all we had to do was do a Docker compose scale, the name of the service, and then everything else was taken care for us. So from an operations point of view, it makes it very simple to scale out any of these particular tiers. Now, when we come to kind of think about persistence and containers, the obvious question is, should we store the data inside or outside of the container? So for most transient type of containers, configuration or transient data you would typically store inside the container. When the container stops, then that data or information is transient and therefore it's lost. So for a database, it might be odd to have that data stored inside the container, because potentially you lose that container or that data when that container is shut down. For an Aerospike cluster, you can define how many replica copies there are of that data, 2, 3, 4, 5. So you could configure the Aerospike cluster so there's multiple copies of the data, so losing one essential copy of that data would not be the end of the world. But that means that when you're adding in new containers, then you have to continually balance across. So more typically, you would store the data for your container outside of the container. So on the right-hand side, you can see a couple of examples. One is to store the data on the host where the Docker daemon is running, and then mount that drive or that device into the container. That means the container is writing the data on the outside of the container, and if the container stops or shut down, is shut down, then you don't lose that data. Restarting the container, you just simply need to remount. The data is already there, and you can carry on. An alternative approach to that is even to have the data volume outside of the host. And so an example of that we can see on the right-hand side, where I'm mounting that data volume from an external device into the container. Typically, that would be maybe something you would consider on EC2, where you'd have an EBS volume mounted into the container, so that data is written outside to the host. So even if you lose the whole virtual machine, you still have the data, and you can then mount that. Aerospike has got a sort of third configuration where we call it shadow devices. So you've got the ability to take advantage of write locally to the host, but also shadow those writes out to an external device like an EBS block store. The kind of rationale for doing that is that it gives you durability if you lose those hosts, but it also gives you the operational advantage that you can use features of that external storage like snapshotting in order to perform things like copying or backup and restores. The bottom line is that you've got several ways that you can achieve this with containers and Aerospike. It really comes down to what are your operational needs. Typically on the left-hand side, you'd see that for dev test, where there is no big loss if you lose that data. For production, then you want to ensure the resiliency of your data. Therefore, you've got a couple of choices of how you would store that data. Okay, so quick summary. We think Aerospike gives a great solution for database persistence from dev to production. We think containers are great for defining and encapsulating everything you need to do. And if you use some of the techniques that we described in this webinar, it means that you can start off simple in development, and as you go through the various stages, you can inject behavior or other constraints so that your operations team or your DevOps team can actually deploy these containers in the way that meets all of their needs. So finally, we'll do some Q&A. The code that we demonstrated today is up on GitHub in terms of the demo. Obviously, we've got our Docker images, and feel free to reach out to me via email or via Twitter. And we're going to be sending out an email blast at the end of this with a link to the recording of the video. So if you want to replay any, you can. So that leads us on to some Q&A, and I see that there is a whole bunch that are all queued up for us to talk about. So where should we start, Richard?
All right. One of the questions that just came in is, can we scale up and down the tier-based system based on system utilization?
Great question. So, you know, obviously in Docker, you've got the ability to add those containers. The orchestration piece, so this comes down to kind of how you want to do your orchestration and how you want to do the provisioning. So out of the box, if you wanted to scale up your services using Docker Compose, that's something that you either have to script or do by hand. If you're using things like Mesos or Kubernetes for the orchestration, then you can start baking those policies into those frameworks to allow you to automatically take care of those needs to both scale up, but also to scale down too. Okay,
you just mentioned Mesos and Kubernetes. Is there any sort of support plan for those platforms?
That's question two. So, you know, we talk to many of our customers who are in the process of using Docker to manage the life cycle from dev to production. Sort of Mesos and Kubernetes, it seems to be the kind of Coke and Pepsi of orchestration, in that we see people who want to use one and are clearly choosing one or the other. You know, Kubernetes tends to, you know, the feedback I hear is that Kubernetes is very opinionated, and if your opinions match, it's a good choice. And equally, Mesos solves a slightly different set of problems. What we're looking at is the best way to support both of those, and what we're trying to understand from our community and from our users in kind of which order we should do that. So it's still work in progress. And if you've got a opinion or even a strong opinion, please reach out and mail me or drop me a note on Twitter which one you think we should be doing next. We're all ears.
Okay. How about hosted container services?
Hosted container service, yeah. So there's a number of companies out there. Obviously, Amazon with ACS. You've got Containership. Docker recently acquired a company to do hosting of containers. Ultimately, what we have shown is using the core ingredients that Docker provides. To do testing as well. This is the basics of described are also used by all of those services as well. So nothing we've shown today excludes you from using any of those hosted services. The fact that you can do clear network differentiation. So you can have the Docker services for the database for Aerospike running on completely different networks from other services. Typically, you need this to provide some separation of concerns. Many organizations we work with have separate security domains for the different levels of data or the different types of data they want to manipulate. Now, clearly, with web page counters, there's nothing particularly proprietary we're capturing here, so we could have done it all on one simple network. But what we really wanted to show today is the power of multi-host networking. We can